Hopefully there's sound. Sorry. Okay, maybe my videos the other day didn't have sound either. That's gonna suck. Okay, so here we have delta G for ammonia and nitrogen and hydrogen, and just like for delta H and delta S, you can use the summation of the products minus the summation of the reactants. So the only thing to remember is that you do have to use the coefficients. Yes? Another thing I'd like you to notice is that delta G, for any element in its standard state, delta G and delta H for any element in the standard state is 0 kilojoules per mole. So even though we have 3 times the delta G of H2, that number there is 0, so it doesn't actually amount to anything. And so this one is also 0. Is good? Is this spontaneous or non-spontaneous? Spontaneous. And K would be larger than 1. Gesundheit. So apparently making noise when you sneeze is just like a cultural thing. It's a learned behavior. It is not indeed the natural state. So if someone is deaf, they don't actually make a noise when they sneeze because they haven't learned that that's what you do when you sneeze. Now, I could be wrong on this because I learned this from QI, where they have all sorts of wonderful facts, but some of the times their facts are wrong. So it could be wrong, but I thought it was interesting, so I thought I would share it. Anyway. All right, let us use this information in the table below to determine, will NH4NO3 solid dissolve in water at room temperature? So you'll notice that I didn't give you delta G, and I didn't give you like an overall delta H and an overall delta S. So you're going to actually have to calculate the delta H. Probably you won't get one like this on the AP exam because I think it's too long for too little, like, meat in the question. Do you know what I mean? But if you did have to do it, you would calculate delta H using, delta H of formation for this one, delta H of formation for this one, and delta H of formation for this one. So you would add them all up, right? We've got 1 mole, 1 mole, and 1 mole, and 1 mole. And you add them all up, and you get a positive delta H value. You would do the exact same thing for your delta S, products minus reactants, making sure that you use the coefficients. In this case, they're all 1, so that's pretty straightforward. Yes, 1, 1, 1. Oh, this should say S. Yes. 30. And that should be an N. I don't know what happened with this one. I just copied and pasted this from somewhere. So not even my own typo. That should be an N, and that should be an S. And there shouldn't be an F down there, but that's okay. I'll go through and I'll make my own version of this later, but it was too hard to type it out, so I just copied and pasted it. And then we are going to calculate delta G. Now, you need to take care because they gave you the temperature in degrees Celsius. Can you use degrees Celsius when dealing with Gibbs free energy? No, it has to be Kelvin, so you're going to add 273.15. If you don't remember that number, where would you find it? On your data sheet, probably in the gas section, I think, because it tells you the gas constant and it tells you STP. That's 0 degrees, okay? So if you forget that number, it's there for you. And now you go, okay, that's great. I also have to remember that delta S is not given in kilojoules, it's given in joules. So if I try and have my delta H in kilojoules minus T delta S in joules, that's not going to work. So I need to convert delta S into kilojoules per Kelvin. We have delta H. You see why I think this might not be a question? Because it's so long, right? And then you check everything in. I just put those there because I wanted to remember what they were. You throw them into delta G equals delta H minus T delta S. And we get a negative delta G. Is it shocking to you that NH4NO3 will spontaneously dissolve in water at room temperature? Shouldn't be, because all ammonium salts are soluble and all nitrate salts are soluble. Okay, here is a solubility product. We have this KSP of lead 2 iodide is 1.4 times 10 to the minus 8. So we have a K value. So you're going to use the equation that involves the K. So you look on your sheet and you say, where's the one with the K? Oh, I go down to thermodynamics. Ah, here it is right here. Yes, delta G is equal to minus RT ln K. Okay. So that's the one we're going to use, and then it's pretty straightforward from there. That's the equation we're going to use. Which R value, because you are given 3 different R values on the data sheet, right? If we go back to our data sheet and we go up to our gases and we look at our R's, there are 3 different R's. Which one will you use when you are working with Gibbs free energy? The one with the joules. Yes, because you're dealing with energy, you want to use the one with joules. So the very first one, okay? So like I said, none of these are really hard because you're just plugging numbers into a formula, but just make sure you know you're using the right R value. You're converting all your joules into kilojoules. You're putting your temperature in Kelvin. Yes? So we're going to use our first R value here. We need to convert to Kelvin. There we go. And now all you got to do is plug it in and be able to use the ln button on your calculator. Okay? Throw it through. If they don't ask you to do it, you could leave your answer like this. But it would be more usual to write it in kilojoules because delta G is usually given in kilojoules. Did I change? Oh, hold on. Where is it? Oh yeah, because you get joules here. You get joules. Delta G, because then we got the joules in the RT. Yes, so it'll give you a value in joules. So, but if it didn't say give the answer in kilojoules per mole, you could just leave it. Okay? Delta G is positive. Oh my God, we finally found a positive one. What does that mean about the solubility of lead iodide? It's not soluble, and its K would be less than 1. Excellent. All right, we now are going to do the reverse process. We have a reaction here. And we are told that our delta G value is 173.4 kilojoules per mole, and we need to find KEQ. So once again, we are relating KEQ and delta G. So you go to your formula sheet and you say, oh, which formula do I use? I use delta G is equal to minus RT ln K. Yes? Which R value should we use? The one with the joules. Excellent. What do we have to do to our temperature? Turn it into Kelvin. And because our R is in joules, what do we need to do to our delta G? And remember, delta G is 173.4 kilojoules. What do we have to do to delta G before we throw it in that formula? Convert it to joules. You could also convert your R value to kilojoules, but whatever. Okay, so we're going to convert delta G to joules. You can show your calculation either with unit cancellation, or you can just be like, okay, I have 173.4 kilojoules per mole, and that's equal to 173.4 times 10 to the how many joules? 3 joules per mole. Only do that if you know you're not going to get the negative and the positive mixed up. Okay, if you're going to get them mixed up, actually do the unit conversion. But if you're not, you can just go ahead and do that. Okay. So, solve for ln K, or you can solve for K, but because it looks a little ugly, I'm going to do it like I'm just going to solve for ln K, and then I'm going to plug it into e to the x. Yes? So this is ln of K. And again, do you need to write in all your units? Yes, you do. Oh, look, I have joules and joules. I have moles to the -1, moles to the -1. And I have Kelvin and Kelvin. Oh my God, I'm left with no units. Is that okay? Yeah, because it's a K. K has no units. So ln K has no units. Yes. Yeah, that's fine. Yeah, you want to show them canceling. Yeah. All right. And now we have K is equal to undo a ln, you take e and raise it to the power of whatever the thing is. Yes? So K is equal to e to the power of blah, 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 blah. Make sure you know how to use that button on your calculator. Check your calculator right now if you've not used it before. Make sure you know how to do it. Call me over if you don't. Wow, that is a terribly, terribly small K value, yes? Is this reactant favored or product favored? Reactant favored. This is very, very not spontaneous. Yeah, okay. All right. What else we got here? Let's review Hess's law, shall we? So how Hess's law works, it's actually really hard to find examples using Hess's law for delta G. I don't think you'll come across it, but I really wanted to review Hess's law with you just to make sure you feel good about it. So I'm going to give it to you here, all right? If you can add up these three reactions, you might have to manipulate them first, and you might have to manipulate their delta G values. If you can add them up to get this, then you can add up the manipulated delta Gs. Yes? So what we're going to try and do is we are going to try and make this out of these three. Yes? So how do we make this out of those three? Well, I would start by saying I need an NO2 in my reactants, yes? So, oh look, here's some NO2 in the reactants, but unfortunately, there are two of them. So what I'm going to do is I'm going to take this reaction and I'm going to multiply the whole thing by what? A half. Okay? Now, I also need an NO2 in the reactants. Is there somewhere where I have an NO2 in the reactants? No. Do I see NO2 anywhere? Yes, I do. I see it in the products. Excellent. So what am I going to have to do with this reaction? I'm going to have to, number one, flip it, and number two, because I've got a 2 there, what else am I going to have to do? Half it. Okay, so we're going to flip. And we're going to multiply by a half. Okay, so I'm just writing down what I'm going to be doing with them. And then finally, I need to have 3 NOs in my products. And this makes me a little unhappy. And I picked one that was nasty to do as an example. It usually you'll just be like, oh, I just do this, 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 and it all works out, and boom, Bob's your uncle, yes? But I picked one where it was like, oh, I've got NO here, and I got NO here, and that makes me a little uncomfortable, yes? So what I did is I said, oh, I will not panic. I'm going to put this one and this one together, and then I'm going to see what I need to do with reaction number 2 to make it all sort itself out. Does that make sense? So don't panic. Just be like, I'm going to deal with what I've got, and then I'm going to deal with the next one. It will all work out. Have faith, because it always will. These are nice that way. So here we go. So we have flipped reaction 3, or sorry, we've got half of reaction 3, and we've flipped half of reaction 1, and now I've added them up, right? And I say, oh, that's grand. This is what it gives me if I add them up. I actually don't want an O2 in the products, right? My overall reaction, is that right? Yeah, I just forgot to cancel it out down here. This shouldn't be here, this is gone. Those got canceled out. Scribble that out. So I look at the reaction that I want, which is this one. Okay, it's the same one back at the top, up here. N2O plus NO2 gives 3NO. So I want to end up with this. And I know that I have an O2 that doesn't belong in the products. Yes? Well, I'm just going to focus on the O2. I'm not going to worry about anything else. I'm just going to be like, I don't care. Nitrogen, whatever, NO, whatever. I'm just going to worry about oxygen and say, I don't want the oxygen there. So I'm going to take reaction 2, and it has an oxygen in the reactants. Yes? Which will nicely cancel out the oxygen in the products. Yeah? And by tossing that in, oh, look, nitrogen also just cancels itself out. And I also have NO. I've got 3 of them. Oh my gosh, it all just sorted itself out. So I don't think you're going to get anything that complicated. I think you're going to get it. It's like, I flip this one, I make this one this, I make that one that, and it all just works out like at the beginning. Okay, but that's as hard as it would get. Oh, why is this not on the right page? That's okay. Yes. Yes. Oh yeah, it should be negative, and I probably didn't make it negative. Yeah, that should be negative. Yeah. So that might be a wrong number there. I'm not sure, but you know, you get the idea. Yes? Okay. Oh no, that's okay. Oh yeah, no, this is something else. Never mind. Okay, we're good. That's it. Yes? And now there's just some practice problems there, which you can do as much or as little of as you like. Yes? Whew. We have now done everything I think that you need to do that review. So this gigantic review that you have that has 191 questions, here's my suggestion. Do 20 questions per day. Give yourself 36 minutes to do those questions. Yes? Then take a 5-minute break. Then you can come back and say, what was I unable to do during that time? If there's something that you just don't know, just highlight it and set it aside. Don't get too wound up about it. You can ask me about it next Friday. Yes? I mean, if you want to do some extra study on your own, that's fine, but I also don't want you to, like, you know, hate your break and hate me and, you know, hate life and all those things. Yes? Okay, so, you know, you could maybe spend an hour a day on chemistry, something like that, and it wouldn't be too bad. I hope, fingers crossed. So yeah, you'd spend another 25 minutes or so marking them, making notes of questions you didn't understand, just kind of noting any sections where you're weak. Have we done alloys? I think we did. There's really not a lot to alloys. There's like, do you remember the two types of alloys? There's interstitial and substitutional. And quite frankly, the name says it all. Yes? When you have substitutional, you are substituting. So if here's your metal and you have a substitutional alloy, similar sized atoms, you'll put them in, like, and they'll just slot in where the regular atom would. So this might be gold, this might be silver. They have a similar size, okay? Interstitial, what does the prefix inter mean? Between. So look, you didn't even need to know that. I can't imagine that you would have to actually pull this word out of your head. I think it would be like in a multiple choice question where they'd be like, is this an interstitial or a substitutional alloy? Yes? So in that case, you would have your metal and tucked away in various places. In the spaces in between, there's something that's much smaller, okay? And that's it. Alloys tend to make metals harder because they don't slide well against each other. Yeah, we did do this. I remember we did talk about this. Okay, we're good. Do any of the other topics look unfamiliar? Alloys, atoms in the periodic table, bonding, chromatography, equilibrium gases. Yeah, the lab with the colors. It does show up from time to time. So it's worth knowing, and it's easy too. Do you know what I mean? Gravimetric analysis is just like using moles in the lab. Okay, but I put them in their own special category so you could see what a gravimetric analysis question looked like. But I think you'll look at it and be like, oh, it's just moles and stoich. Yes? Yeah. Gravimetric analysis is moles and stoich. We got IMS, kinetics, moles, reactions, and stoichiometry. Semiconductors, there was one question about 8 years ago. Anyone really concerned about semiconductors? If you are, we can talk about it later, but I think we should not spend time. Solids, solutions, electrochem, spectrophotometry, thermochem, and thermodynamics. Casey, you had a question. Oh, that's going to be, okay, do you remember how we had that one question where it was like vibration and rotation and which one did which? And you see how there's only one question on here? The other one, there's only been 2 questions, and the other one is on that worksheet that I gave you. So it was, I think we did we do it in equilibrium? Yeah, because it went with entropy. I just sort of talked about it in entropy, because it has to do with the right vibration and the rotation. Remember, the thing in the microwave rotates, so microwaves cause rotational, and V equals I times R, so vibrational is infrared, IR. But honestly, I don't even think you'll probably need to know that. Ultraviolet, those are going to be electron transitions, okay? And do you remember seeing those like glow tubes, like with the elements in them? Yeah, you know how we put electricity through the thing and then we looked at it with the glasses on? No? Maybe Science 9? Okay, maybe I'll haul them out before we write the exam, I don't know. Anyway. Thermodynamics includes delta G and stuff. Thermochemistry is just like delta H. And what's what? Kinetics is reaction kinetics. That's reaction rates. That's rates. Yeah. Okay. So that's my suggestion. Let's do some solubility in the last 20 minutes. Okay. So did you guys watch the video? Yes? How did it go? Pretty straightforward. I thought so. I was hoping it would be. Where did we get to here? I don't want that one. So, do you need me to go over this, or do you feel like you are good and you could just do some practice? What do you think? You feel good? Okay. And we already did finding solubility from KSP, right? And then we have minimum or maximum problems. And I'm going to skip over the video part here, would you rather watch the video or would you rather have me teach it? Teach it? Okay, so we're going to skip over this part. You can watch it if you feel like Ms. Spence didn't do a great job. Okay. Keep going. Okay. Work through the following minimum problem. So these are problems where we are looking for the minimum amount to just start precipitation. This is on page 72. The key thing with minimum problems and maximum problems is that they both exist when the ion concentrations multiplied together exactly equal KSP. Yes? Because if you say, what's the maximum I can have without a precipitate forming? You're like, I'm adding and my ion product is getting bigger and bigger and bigger until eventually it's going to hit KSP. And once it hits KSP, it tips over into a precipitate forms. Yes? But right when it's equal to KSP, you can say, that's the maximum I can have without a precipitate forming. But it is also sort of the minimum I need to just barely start precipitation. The distinction is going to be like 1 drop. So you can just use that for both, right? Even though like one's going to be just one side of the line and one's going to be the other side of the line, you just use it. So essentially, these are the easiest problems of all because you just need those 2 ion concentrations to equal KSP. And you're going to be given KSP, and you are going to be given one of the ion concentrations. So you have an equation, KSP, you have a KSP, you have an ion concentration, you got 2 variables, solve for the third one. For some reason, these questions sometimes freak people out just because they want to complicate things, but they're actually the easiest. So let's try this one here. So we have copper iodate, so that's going to become Cu. 2 plus 2 IO3 minus aqueous. Oh, and I guess I should read the question first. A large beaker contains 2 liters of a 1 molar solution of copper 2 nitrate. What mass of solid KiO3 would need to be added to this solution to just start precipitation of CuIO3 solid? Partially the tricky bit here is that we give you copper 2 nitrate and we give you IO3, and I think people get confused about which compound they're working with. I think that's one of the places people get confused. You are always going to be looking, if you're combining 2 things, you are going to be looking for the low solubility compound. Yes? If you're mixing 2 things, you're going to say, what combination of ions gives me the solid? And in this case, what combination of ions gives you the solid? It is that one. So don't start trying to write a KSP for copper 2 nitrate, right? It doesn't have a KSP, or its KSP is very large because it's completely soluble. Don't start trying to do it for potassium iodate. You want to be sure you identify the precipitate. So actually, before step 1, step 0 is identify the precipitate. And then once you've done that, you can be like, okay, the precipitate is the copper iodate. I'm just going to work with that. And the other thing will just give me my ion concentrations, okay? KSP, that's pretty straightforward. Cu2 plus, IO3 minus squared. And we solve for IO3. So that's going to equal our KSP divided by the concentration of Cu2 plus. Actually, this should say IO3 squared, shouldn't it? And this should say IO3 squared. You could just take the square root of the entire thing. I kind of like doing the math and then taking the square root, but you can put the square root over ahead of time. That's totally fine too. Okay. And then we go to our data booklet and we say, what is the KSP from page 5 of the data booklet? Copper 2 iodate, 6.9 times 10 to the minus 8. 6.9 times 10 to the minus 8 over. Now you have to go back to the question and say, what is the concentration of copper? Well, we have 0.1 molar copper 2 nitrate. So what is the concentration of copper? 0.1 molar. 0.01 molar, sorry. 0.01 molar. Exactly. Yep. And we just plug that into our calculator. So we have 6.9 times 10 to the minus 8 divided by 0.01 equals, and then we'll take the square root of that. And we get 2.627 times 10 to the minus 3 molar. Here's the thing that people find it really tempting to do. They look at this equation here and they say, oh, copper is an iodate, it's a 2-to-1 ratio. So if copper is 0.1, then I simply know that iodate must be 0.02. Why is that not the case? Chat amongst yourselves. Why is it not the case that iodate is twice the concentration of copper? So where is the copper ion coming from? Comes from copper nitrate. Which is 0.1 molar, yes? Where does the iodate come from? And it goes in as a solid. Does it have any relation to the copper nitrate? No. So that's why it's not twice as much, because it is not coming from copper iodate, it's coming from potassium iodate. Does that make sense? This is what we call, do you remember we talked about that mix and match? Okay, so when you dump and stir, if I was to take copper iodate, salt, and dump it into a container, you would end up with 1 copper and 2 iodates, because they all came from CuIO3 But here, we're taking copper nitrate, so you get a certain amount of copper, and we've got our iodate from KiO3, and we're dumping them in separately, so their ratio can be anything really. Yeah, because they're coming from different places. So we get to the end and we say, okay, that's grand, I have a concentration. I need to now find my mass of KiO3, right? Because our question asks for the mass of KiO3. So we could find our moles of IO3, 2.627 times 10 to the minus 3 moles per liter. Whoops. What's our volume? It's the 2 liters, and normally they will often say, assume that the solid doesn't change, the additional solid doesn't change the volume. Even if they don't say it, you can just make that assumption, because otherwise it makes the question impossible to do. Okay, so it's still 2 liters. .25 times 10 to the minus 3 moles. And then our moles of KiO3 is the same. Why do I have so many steps here? I think it's because it's part of the video. Do you have to show this conversion this way, or can you just say they're equal to each other? You can just say that they're equal to each other, but that's how you would show it. And then your mass, 5.25 times 10 to the minus 3 moles of KiO3 times whatever the molar mass is, grams per mole. I don't know what it is. Whoa, what happened? That was crazy. Okay. And apparently it equals 1.1. So when your ion concentrations multiplied together exactly equal KEQ, you're going to just start precipitation, or that's also the maximum you can have without precipitating. Is good? Okay. The minimum and the maximum are the same, essentially. What you've got is you've got an inflection point, yes? You go from not having it all dissolved, or sorry, having it all dissolved to saturated to precipitate. And we're just kind of like on either edge of that, on either side of that knife edge. So we just consider that knife edge to be the place where either you can add that much and the precipitate won't form. In fact, if you wanted to be a little more specific about it, you could say I would need, in order, the minimum would be just more than blah. But quite frankly, in the lab, we can't usually get that accurate with our measurements anyway, so you can just kind of be like, okay, it's the same regardless. Yeah. Yeah. So here's just that little knife edge, yes, that we were talking about. Where'd my pen go? There it is. When Q is equal to KSP, the solution is just barely saturated and no precipitate forms. So it doesn't matter how you ask the question, we use the same calculation. And it's the easiest one of all. Just don't make those silly mistakes of like trying to make the ion concentrations proportional to the coefficients. Okay? And don't try and find the KSP for a soluble compound. Always look for the precipitate. So you can see step one, identify the precipitate. Oh, look, we're writing the C again, we're writing the KSP. All you do is plug in the KSP and one of the ion concentrations, and then if you need to find moles or grams, off you go, and Bob's your uncle. Yes? And I think other than titrations, that's pretty much where we're at. Did you want to do one more example, or do you feel like you're okay? How are we feeling? We can do one more, sure. So what is the maximum mass? This is page 74. What is the maximum mass of Na2SO4 that can be dissolved in 1 liter of 0.0500 molar lead nitrate without a precipitate forming? Step number 1, we identify the precipitate. Who is our precipitate? PbSO4. Excellent. Write the SEE, the solubility equilibrium equation. That's just my thing. Nobody else calls it that, but you know, me, I'm lazy. Okay, PbSO4, solid equilibrium, Pb 2 plus SO4 2 minus. Write the KSP expression. And then plug in the values. So, do we know our KSP? Yes, we do. We know our KSP because it is on our data table. In AP, it would be given to you in the question. Lead, what? Lead sulfate. There it is, 1.8 times 10 to the minus 8. You can solve for SO4 first, it doesn't matter. Concentration of lead, 0.0500 molar. Concentration of SO4 2 minus. You can write X here instead, but you can also just leave it as SO4 2 minus. Yes? Oops. I don't know that it matters, blah, 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 blah. Okay. And so then you would just solve for SO4 2 minus. I want to get rid of my molarity because that's not happy in a KSP. 3.6 times 10 to minus 7 molar. Then we would just convert that to, because we're going to run, our bell's going to go in like 1 minute, we would convert that to moles times 1 liter. And then we would convert it to grams times the molar mass. Is good? Okay. So study for your quiz for tomorrow? Yeah? And then tomorrow we'll look at sorting out all the solubility problems, and then we're done solubility. We might even finish solubility tomorrow. Huh? There's parent-teacher interviews. Yeah, no, don't forget Friday, when do you arrive? 8:40 on Friday. 8:40 on Friday. Don't show up at 8:40 tomorrow. I won't be teaching you, okay? Just on Friday. Okay. Friday at 8:40, Harry. Which is tomorrow. Oh my God, I can't do, I'm saying the wrong thing. Do show up at 8:40 tomorrow because tomorrow is Friday. Silly me, sorry. I'm saying things that make no sense whatsoever. I thought today was Wednesday. Now I have to talk to parents and pretend I can make some kind of coherent sense. Yes?